Hello friends, today I will discuss how to solve first order ordinary differential equation using MATLAB and Simulink. Simulink, as we all know, is an extension of MATLAB and is used for modeling, simulating and analyzing dynamic systems using graphic user interface. So in our problem, let's see a first order ordinary differential equation, which is a simple mathematical problem, that is dx by dt is equal to minus 2x plus 1 for t greater than 0, and initial conditions are at t equal to 0 the value of x is 0. So in this problem, if we integrate dx by dt over the time period from 0 to t, what do we get? We get xt, which is x a function of t, the output, with the initial conditions as x at 0 as 0. So we'll try to approach this thing using Simulink. In Simulink, we have a block which is named as integrator. I'll show you to you later on where it is. Now in this block there is an input sign and there is an output sign. To this integrator, the input is our differential term, that is dx by dt, and the output will be our function x, which is basically, this is what it is happening is we integrate dx by dt, we get xt. Simply again in this integrator, if with the input is dx by dt, we'll get the output as xt. Now let's move to the MATLAB window. Okay, this is the MATLAB window. Now in this MATLAB window, this is the command window where we write down the commands, and over here your file is being saved. Okay. Now if you see, look at this red button over here, this is basically a Simulink icon. We click this. Now this library gets opened. This is Simulink library where different models, different blocks have been created. Commonly used blocks, continuous blocks, discontinuous, discrete, signal routing, sync and source. Now if we look at this icon, which is a new model icon, when you click over here, a new window gets opened. In this window, we'll try to create our model that will represent our first order ordinary differential equation. Now to this model, first let's put this integrator. What we do is we simply click this and drag it over here. Now this is our integrator. Now in this is the input signal and this is the output signal. Okay, so let's extend this. Done. To this integrator, obviously we're going to add something. We'll get some output over here. That output will be stored in this scope. We'll have a scope over here. We can simply drag it somewhere and then reconnect this thing. Then we require a summation sign. I'll tell you later on why we require a summation sign for this. We need a constant term also, which we'll drag it over here. And then we require a gain also. This is the gain also. We'll close this window. We'll try to relocate this. Okay, we have now two gains. We'll try to relocate this, format this, rotate a block in the clockwise direction and again in the clockwise direction. Done. Now we'll take a look at our equation. Now this is our equation, that is dx by dt minus 2x plus 1. Now in this model, let's minimize this thing so that the equation at the same time is clear to us. Now this is the dx by dt. This goes to the integrator. It gives me x as a function of t. Now this x is a function of t is multiplied with this gain we'll double click this gain. Now this a new window open where we can assign any value to this gain. Now in this window we have the x value as 2, so we'll write 2 over here. Okay, then this gets connected to this summation sign. Now we double click this summation sign, and over here it's plus plus, so we can see plus plus in the summation sign. We can change it accordingly. We can write minus, so that means this minus 2x, this 2x gets added as minus 2x. We can see minus sign over here, so it's minus 2x plus 1. The constant value is obviously the 1 because we have 1 over here. Now both 1 minus 2x is equal to dx by dt. So this is our differential equation. Now we're in this integrator sign. When we double click this, this block parameter of the integrator gets opened up. Over here it's written initial condition. We'll write down the initial conditions. So value of x was 0, so we'll assign the value as 0. By default value it's already taken as 0. Okay, now we can see this entire window, this entire model has been created and all the blocks have been connected properly. So then what we're gonna do is we'll try to save this. Okay, let's save this model by some name. We name it as ODE, simple ODE model. So over here an ODE model has been created. Clear? Now since all the connections have been done, now it's up to us to what time interval we want to run our model. So by default the value has been taken as 10. We can increase up to 100, we can go up to 50 also. Then if we click at this simulation, we go to this configuration parameter. Over here the solver starting time is 0. Okay, we can set it at 1 or 2 or 3, whatever we want. Stop time is 1. The methodology which is solving is the ordinary differential equation. That is basically a Rangakuta method. Maximum minimum size, it has already been defined as auto. So it will automatically define the step size according to this time interval. Okay. Now let's try to run this thing. So in order to run this, we'll click up this play button. It says start simulation. We click this and a model has been successfully run. Now in order to view the result, what we do is we click this scope. So when we click the scope and this scope window opens, we can resize it, let's maximize it, and we can click this binocular button, which is basically an auto scale button. When we click it, it shows the profile. So we can see over here, this is the time axis and this is the value of Rx. So at t equal to 3, it reaches the value of 0.5. So after t greater than 3, all the value is constant, that is 0.5. So this is the solution to our differential equation using Simulink model. Now there is an alternative method also for this. For that, what we're gonna use is we're gonna use the help of transfer functions. So we take a look at our equation, which was dx by dt minus 2x plus 1. Over here we have assigned a value of 1 as ut. I'll explain you later on what is ut. Dx by dt, we define a differential operator d. So we club the x terms together, x common has been taken out, so x is the output, which is 1 by d plus 2 into u. Now this 1 over d plus 2 is the transfer function, and u has been assigned a value that initially at t less than 0 it is 0, and when t is greater than 1 it shows the value as t greater than 0, it shows the value as 1. So again the same model can be created now using the transfer function. We can see over here the constant, the transfer function, that is in our case it's 1 over s plus 1, and the slope. So let's try to again represent this model, the MATLAB. Okay, so again we'll click this directory, new model, will from the transfer function we have this transfer function, the common blocks, we have a constant value and the scope. This is the scope. Close this. Now we'll connect all these terms. Now our model was 1 over s plus 1 transfer function. 1 in the numerator, now in the denominator we want s plus 1. So we'll write 1 for s, constant 2 for that, and the constant. So this is again model. So we'll again try to save this by a name. Let's say ODE alternative. Right. Save, and we'll try to run it. Again done, and again it shows the same result. That at t greater than 3, the value is 0.3. So we can solve a same problem using a transfer function or by using a simple. Then there is another alternative solution to this, that is using a command, that is sim command. Now this sim command is basically a command which will be written at the MATLAB command window, and the procedure of writing is this, that is txy is equal to sim, that is simulate a Simulink model name, time span, and these are optional terms. Now I'll show you one example for this case. Okay, it is this thing, that is this is the command which we're going to write at the command window, t comma x equal to sim our model name. Since in this example it's example 7, so example 7, and then we'll say plot t index, so it shows this plot. Now let's try to run at the command window over here. Well, first let me clear this. Okay, alright, t comma x is equal to sim, that is simulate a model. I'll name the model. Over here I'll have two different models, I can use any one. Let's use ODE, inverted comma, close, and arrow. So the model has been run successfully. Now I want to plot this plot. So plot command t comma x, and this is the result. Again it shows the same result. That is, we can see over here the time axis and the value of x, and again at x greater than 3 the value of x is 0.5. So similarly, same problem can be now solved using a sim command also. So this is the third method how to solve the ordinary differential. We have another method where we'll use basically the MATLAB commands to solve our ordinary differential equation. Now for that, what we do is, on this command prompt window, we'll write a name, let's say ODE1, which is, we'll write down the differential equation in this. That is written by capital D, x is equal to minus 2 x plus 1. This is our ordinary differential equation we have defined in the command prompt window. We'll give the initial conditions, that is x equal to 0, okay, shows this thing. Then we'll say x is equal to d. So this is the command that will solve our ordinary differential equation. Now it shows we have to insert the equation. So in our case it's basically ODE1, the model which we have created, comma, and the initial conditions, and it's the end. Okay, there is an error in this, so let's write the spellings are correct. Now this is the equation. So let me clear this again and rewrite the things again so that everything is clear. Okay, and done. We can use this command. So it shows this. So this is the result. So we can see as t approaches infinity, This term goes 0, so we have half, and that was the result which has been shown by the Simulink model. Now we define the time span 0 to with a step size of 0.1 to 10. Now we'll say axis, which is evaluate, vectorize x. Now I've used vectorize because over here t is a matrix and it will pick up, x will pick up all the values of t. So in order to pick up all those x values of t, we have to define a term vectorize. Let's run. Now we can use a command plot t, and there you have it. Again the same result. So we can see we can solve first order ordinary differential equation using 4 different methods, using Simulink, using MATLAB windows and commands, and using the combination of MATLAB and Simulink using the sim command. So dear friends, thanks for watching. For any suggestions and query, you can mail me at this email ID. So stay tuned for another video that is for second order differential equation. Thank you.